Okay, well, I will give my description of this, and then perhaps Gord can expand again. This is, for me, where things get quite interesting. So magnetic imaging can detect the presence of things like our giant cannonball, which is made of metal. It would show up as an anomaly on a magnetic survey. It has a magnetic effect. Actually, somewhere in my collection of objects around me, I have a very rare piece of meteorite. So this is an iron nickel meteorite from Namibia. It's one of the Gibeon meteorites. It weighs about 1.2 kilos, so it will have a bit of a gravity field association, but more importantly, it has a very strong magnetic character. So materials like this, rocks that contain a lot of iron and other magnetic elements, can be imaged using magnetic surveying. You can get some quite nice images of features like kimberlite pipes, where diamonds are found. The ultramafic minerals, as they're known, which contain the diamonds, have large quantities of iron in them, and that actually gives them an opportunity to be able to be imaged by flying airborne magnetic surveys. Of course, magnetism won't help so much if the cannonball or if the rock is made of non-magnetic materials, and that's really where we need to understand the difference between what these techniques can offer us. So in a resource context, magnetism is somewhat limited unless you mix it together with other techniques. So whilst magnetics are extremely helpful for me as a mineral explorer, once you start to pair magnetics with things like gravity and full tensor gradiometry, you suddenly have a much more impressive toolbox with which to play. So to give you the background on conventional gravity as people have used for maybe the last 50 to 100 years, gravity tends to spot quite long wavelength trends in the Earth's surface. So it picks up large bodies of rock and contrasts, which are over many kilometers, many miles. And conventional measurements would tell us maybe that an object of a huge, great piece of igneous rock is present, but it doesn't tell us very much about the shape of that igneous rock, and it doesn't really tell us very much about how deep that rock is either. And as an explorer, knowing how deep something is does matter, because you need to know how far you're going to have to get down into the ground to find it, and whether it's going to be worthwhile mining. So gravity is only really detected in one dimension. You can do it with ground-based measuring tools, gravimeters, or you can fly them in a plane, as Bell do. And so therefore, it's actually quite hard to see the shape of features. If you're looking with one eye, you can't see in stereo. You can't really see what's happening around the back or around the side of the object. So as Gord mentioned earlier, we can have something like a cannonball, which we can image as a sort of circular feature on the ground on a map. We don't really know whether that is truly a cannonball or whether it's actually a big long rod made out of the same material with the same mass. So certain cross sections aren't going to tell you very much about the object. And that's really where gravity on its own starts to struggle. So magnetics and gravity together really, really help. And they've been instrumental in finding all sorts of different deposits around the world. But the addition of full tensor gradiometry, FTG detects the pull of gravity in the third dimension, so you can start to see what's going on from the sides as well as from above. And that really is a huge, huge advantage for us. So we're measuring the rate of change of gravity. So it's not just the actual amount of gravity, it's the rate at which it changes. So I know Gord, I think, has a fantastic example of the difference between a direct measurement and a rate of change measurement. So I won't stray into that. But the key thing is we're looking up and down, and we're also looking side to side. So as a non-mathematician and as a non-expert physicist, I will leave the complexities to Gord to describe. But for me, in simple terms, using something like FTG as a tool is a little bit like having sort of hawk-like stereo vision, as opposed to just looking from a distance and just seeing one-dimensional object. So Gord, take it away.
Thanks, Tim. Yeah, well, the 3D, just to take on your last point, the 3D element is really important. Gravity gradiometry is a full 3D measurement, but we will go back to that maybe. I'll go back quickly to magnetism and gravity. And as you said very well, the main difference, they relate obviously to very different physical property, magnetization and density. And magnetization is inherently more complex than density, and we won't go into the detail of that, but explorers use both, and they don't always see the same thing, as you very well explained, Tim. And for example, you can have rocks which are both dense and magnetized, but you can also have rocks, for example, which are dense and non-magnetized. Carbonates is one example. And you can, of course, also have rocks which can be two rocks which are both magnetized, but will have different density signature. And these differences are not a bad thing at all. On the contrary, as it often makes these two methods very complementary and helps explorer separating, distinguishing different lithology and rocks. So again, integration and complementarities are really keys in exploration, always been and will always be, I think, of method and approach. So let's go back to gravity versus gravity gradiometry. And maybe before even going there, let's go back, Tim, as you say, to the rate of what is a rate of change.